Bismillah ar-Rahman ar-Rahim. This is Dr. Bassam Alhamad with you, teaching chemical engineering course CHENG324 Process Modeling and Simulation, and we are going to be taking lecture 11 today. And our lecture 11 today is going to be talking about Laplace transform. So what we are going to be taking today, we are going to be taking Laplace transform. Okay. So before getting into Laplace transform, what we have done before and what is that related to Laplace transform? So what we have taken before, that was we have developed model equations. So we have developed model equations for a group of processes. And this group of processes, one was the CSTR, if you can remember, and another one was the mixer. Okay, so that is a mixer. I forgot the stirrers, and that is a mixer. And we have taken the surge tank, and we have something like that. We have gas in and gas out, and we are trying to control the pressure in this case. So that was the surge tank. And then we have taken some other examples for the one with the conical tank, and then we have taken CSTRs, tanks in series, and so on. So these are the examples that we have taken. So if you just can recall what we were concentrating on, we were developing model equations to target some process variables that we want to control later, which are very important to know. So in the case of the CSTR, it was important for us to know how does height change with time, how does concentration change with time, and about temperature, how does it change with time. And for mixer, it was important for us to know how does height change with time, and how does the composition also change with time. And for surge tank, the most important thing was how does pressure change with time. However, if we have more than one component, we want to know how does the composition, talking about the vapor composition, change with time. Conical tank, it was mainly how does height change with time. And here we had just studied an example of like two tanks in series without any reaction. So we wanted to know how does height change with time, and the main idea was about the flow rate as a function of the difference in the height or only the height. Okay, so for all what we have taken here so far, if we just have a look, about all that is in time domain. All that is in time domain, and you can see the time domain that all of them have dt. Okay, so they change with time. So what is Laplace transform to do? What we do here is we undergo some kind of Laplace transform, taking it into a two-new dimension, where we call this dimension the S domain, okay, or the Laplace domain, whatever you want to call it. And you have already taken that in your earlier course. I remember the name of the course was differential equations, if I could remember. So what you're trying to do, you're taking Laplace transform to go to the S domain, and the Laplace transform, if you can recall that that was the definition of it. S is equal to A plus J omega. So you're talking about real and imaginary axis. So you're taking it into a different dimension. And when you take the Laplace of a function, and if you say the function, for example, we're going to take the simplest example, if f of t is equal to 1. So in this case of f of t is equal to 1, we are just taking the example of f of t is equal to 1. So Laplace of 1, and then you're going to take the integral of 0 to infinity to e to the power minus st minus multiplied by the f of t. So we are multiplying with an exponential term, and this is where you're trying to take it to a new dimension, and taking the limit with that dimension for e to the power minus st dt, and after solving that problem, we obtain this equation here. And by the way, all of this is not requested for you to know by now, because we want to concentrate more on the applications rather than doing the integral stuff here. So you can review it if you want, but we are not going to be using that in our course. So what I'm trying to say here, the Laplace of 1 is 1 over s. Okay, but it will be enough for us to use the table. So you just can use Laplace tables. Using Laplace tables, that means the tables that shows to you if you have f of t, the function, if it is 1, then and after taking Laplace, so this is like in this direction, we're going to take, it will be Laplace. Okay, it will be Laplace. And from f of s to f of t, it will be Laplace inverse. Laplace inverse, and we represent it as like that notation here. So if we go back and say what is the Laplace of 1, it is 1 over s. So you directly can do the Laplace without doing the math that we have just done earlier here. This is just a reminder of what we have before. So again, so why we are taking it to Laplace, because it helps us to solve the problem. So why Laplace? Why Laplace? We Laplace because it solves the differential equation, and actually it helps us in the analysis of the system. And you're going to see the analysis of the system and the beauty of it later when we go into depth of this course. So the analysis of system, when you say that, well, you can know that if the system is stable or not. Just by taking Laplace and looking at the system, you can see the effects of changes of inputs. So if you open the valve and the height will change, how fast or how slow, you can even study that. So the beauty of taking Laplace into different dimensions, that you can do a lot of analysis. So going and looking at what do we need from Laplace. Okay, so Laplace tables, there's a lot to study there. So what do we need from Laplace tables? Well, I like to put my Laplace tables into inputs and outputs, and actually you will not find this on the net, but this is the way how I look at it, to know why we are concentrating on these functions. There are like many functions, there are many f of t. If you put, so there are many f of t's, there are a lot. So why we're concentrating on certain f of t, and you're going to get the idea in a moment. So talking about different functions, well, if I draw my system here for a tank, and you will see that you're going to concentrate on a tank because it's good for analysis and very easy to understand. So this is a tank that we have here, and just to say that we're trying to control the height. You are trying to control the height in the tank. And how do you control the height? You start manipulating the output of this valve. So if the height goes higher, you're trying to well, let me say it went up to here, to this level, higher. So as it goes higher, what you're trying to do with this valve, you're going to open the valve to have more liquid outside, so this drops down. And if it goes lower, we'll try to close this valve so that it goes up again. Okay, so what you're trying to do here, open or close the valve, it's like you're taking it from a certain position to another position. So what I'm trying to say, so if the valve was 20% open, for example, and you open the valve to a new position, which could be, for example, 30% open, we call this a step input. You call that a step input. And a step input is represented as a number that goes from one position to another position. Okay, so a number. So how much did it jump? It jumped 10. It jumped by 10. 30 minus 20 is equal to 10. So a number. So the first thing we're going to target here is if we have an input, which is like a step input, we have a step input, and usually step inputs are numbers. So if you have 1, for example, the f of s after taking Laplace will be 1 over s. And if it's 10 in our case, it will be 10 over s. And if you want more details, you can go back to the PowerPoint presentations that explain Laplace in details. Okay, so this is like why we are taking the number and the Laplace of it, because it is important. We do have changes in valves in this case, as the case that we have in the valve. There is another application that is not very popular, but the change in the valve could be linear. Linear in what sense? Is that we have the valves changing in a linear format, something like that, continuously changing. And actually the application to a valve here is not accurate, but for example, you have the concentration of a certain substance as being leaked to the atmosphere in a linear format. So that is a linear format. What will happen to the concentration of that vapor in the atmosphere if there is a leak which goes in a linear format? So they call this change as an input, and then we study what happens as an output as a ramp input. So the first one was called step input, and the second one is called ramp input. So here, when I talk about ramp input, and ramp input is represented as T. So I'm talking about T as just a slope. So here, if I have T, I'm just going to shift to white. I think it will feel better for you. So if we have T as f of T, if we change it to the S domain, it will be 1 over S, 1 over S plus 1. No, it will be, the answer will be 1 over S squared. Sorry for that. So it's 1 over S squared, and actually it's 1 over S to the power n plus 1. So that I missed that. So T will be 1 over S squared. And if it's going to be in a different format like T squared, it will be 1 over S cubed. And you're going to include the factorial, the factor at the top. So it will be 2 over S cubed. So what I'm trying to say here, that T to the power n, if you take it to the Laplace domain, it will be n factorial over S to the power n plus 1. Well, what is the most important thing that you need to memorize? You will have the Laplace table, but what you need to memorize out of all that is this, because this is a real thing that happens in life, and the rest are just things that we may use them for a certain reason to go back to our T domain, but to go to the S domain, this is the one which is as an input is applicable. And of course the first one, which is that one here, 1 to 1 of S, which is a step input. So these are very common inputs that we must know and follow. We have also another type of input which sounds strange for a moment. You can have an input that looks like that. Oh my God, how can this happen to a valve going up and down and up and down? Things could happen in this shape due to due to valve stiction, and you could have something like that happening, going like a sine or a cosine wave. But actually, this is not really very applicable, or it's not applicable. That is not popular that it happens in the industry. But if you think of a moment, these kind of inputs look like sound waves. And who does study sound waves? So the electrical engineers could study this as a sound wave for an input. So a person who has a microphone, and is this a microphone? Okay, so let's draw it again. So a person with a microphone here, and he is just talking loudly, and this comes as an input for a sound wave. What will be the output? Okay, as the change in the input. So his sounds changes. So there's an output out of this thing that is getting out to the people. So what I'm trying to say here, the input that I have is a sine wave. So we need to consider that if I have a sine input, a sine or a cosine input, so, and because I'm talking about sine and cosine input, it's important for us to know how does that how is that represented in the time domain, and then how it is represented in the S domain. In the time domain, it is represented as sine AT. Okay, sine AT, and this is represented in the S domain as A over S squared plus A squared. And for cosine AT, this is represented as S over S squared over A squared. So now you know the reasons why we are concentrating on these inputs, these kind of changes that we have. Actually, we also use it as a part of the output, but this is what we have usually. Well, this is talking about the inputs. For a moment, let's continue. What else do we have? What else? There are some other outputs we also want to study. So what else we are talking as an output? Well, if anything, if due to this change in height, for any reason there's a problem with this valve, or there was a change in this valve, this height is going to be changing. The height is going to be changing up and down, up and down. So what is the change? There was a change in the valve, and then the output was changing. Usually the output, as you already had seen in many places, the output looks something like that. For conversion, for changing concentration, or it goes from one steady state value to a new steady state value. And this is something like it looks like what looks like an exponential term, where either it goes from an old value to a new value in the positive side or negative side to a new value. You're talking about an exponential term. And because we are talking about an exponential term, so we need to know if we have an exponential term in the time domain, how it will look like in the S domain. It will look like something like that, 1 over S plus A. And actually, that's not only the outputs that we could have in our outputs. We could have some other outputs which look differently, and I will draw in the figure here something that looks like that. Just look at it. It is like that. So what do we have? We have a sine wave. However, this sine wave is going decaying till it gets to a new steady state value. So what do we have? We have a sine wave, but the sine wave is decaying. This is represented as sine AT into e to the power minus AT. Into e to the sine omega t, I would say, into e to the power minus AT. So this sine omega t into e to the power minus at is represented in the S domain as omega over S plus a, the whole thing square, plus omega square. And if you go to the cosine wave, which is something very similar to the sine wave, into e to the power minus at, it will be the term in the S domain will be S plus a over S plus a, the whole thing square, plus omega square. So these are the terms that we need to know, and that's the reason why we're studying these terms, the T domain and then the S domain, because they do represent something that we have as inputs or outputs. Of course, we have here e to the power minus at, and this is how it is represented. Well, sometimes we have systems, sometimes we do have systems in a sine wave that look like that. Wow. And it just goes forever, and and this is one, if you can remember that sometimes you hear a microphone and then it shoots out and it hurts our ears, is because it's just going to infinity, and it's growing and growing, amplified, and so on. So in this case, this is an unstable process, right? You do agree that this is unstable, right? And talking about this unstable process that goes on, what's happening here? We have a sine wave, omega t, and this is multiplied by an exponential term. How this exponential term is positive. So if you have greater a, it will not decay to 0. If you have greater a, it will just grow to infinity. And this is why you have something that goes like that and it goes to infinity. And in this case, the only difference that you're going to have is that it's exactly the same. I'm just writing it again. Sine e to the power at. It will be omega, and the only difference is that the s is going to be different, right? Instead of s plus a, to be s minus a, plus omega square. So that is the only change that we have. The minus sign is different. And similarly, if you go to cosine omega t into e to the power minus at, this will be s minus a divided by s minus a, the whole thing square, plus omega square. Okay, so that is why we are studying these systems, because these systems do tell us. We are studying these time domains because these time domains do tell us about something that's happening really in the process, either as inputs, changing the inputs, or it appears as an output. So these are the main terms that you need to know for Laplace and Laplace inverse. You can know more, yes, you can know more. Actually, you will have the Laplace tables. So Laplace tables, there's a lot that you can see in the Laplace tables. And for a moment, if you go to Laplace tables, and you just go make a quick search and look at the Laplace tables, and there are just many of them all over. So that is one of the Laplace tables we would like to look at. So this is a Laplace table. Okay, so that is a Laplace table, and if you look for a moment, that this Laplace table, it shows to you that if we have here 1 as f of t, then the f of s is going to be 1 over s. T to the power n is n factor over s to the power n plus 1. And of course, for the sine wave, what do we have? You could have a sine wave with a ramp change. Is very rare that it happens, and this is how the output will look like. So you can see many different stuff, but I already told you the main ones that you need to be concerned about. So number 19 is important, number 21 here is important, 20 and 22, so 19 to 22, they are important to know. 23 is also important to know, which is a ramp with an exponential term. But other than that, you really don't need to know most of these, or you're not maybe going to be using most of what is in the Laplace tables here. Okay, so these are the most of what we have. There's one last thing that I did not mention as an input, and usually I keep it at the end because like some of you it sounds odd for some of you, so I usually keep it little delayed. So what do I have? We have something as an input called impulse input. Impulse input, and this impulse input is something like it's like a direct function, and this direct function was found to, after you take the integration of it, it's if you take it to the Laplace domain, after taking the Laplace, it will be 1. Okay, and that's just the integration of what is going to happen in your graph. So the impulse thing is that you're having nothing is happening to your level, and for a sudden, maybe the level is not a very good example, it doesn't change that quick, but maybe for the flow there's like something like a spike, there's a change that happened rapidly, and then it just faded away in a moment. Okay, and things are back to normal again. So taking the integration of this part through some kind of taking the integration through some kind of verification, it's not verification, some kind of going through finding the integration under that area, you're going to go through a lot of derivations till you get the Laplace or the integral of the after taking the Laplace to be 1. So simply saying that if you have an impulse input, if you want to show it in the S domain, it is equal to 1. It is equal to 1. So that is the one more thing that you need to know on all of these details. So what do we have? We have taken so far. We have shown what are the most important terms that you need to know the Laplace and the Laplace inverse for. Okay, finally for this lecture, there is one more thing that we need to be considering about. We will also be dealing with Laplace transforms of differential equations. Okay, we are also going to be dealing with Laplace transforms of differential equations, and we need to know how is that dealt with. So the Laplace transform of differential equations, if we take the Laplace of a differential of a normal, before taking the differential equation of a normal y, just y, it will be y. So y is y. So simply y. So that's it. So that is y in the t domain, then that's y in the s domain, and this is just showing here as a function of t, telling you that it is in the t domain, and is here as a function of s, telling you that it is in the s domain. And if you want to take the Laplace of dy by dt, so you're talking about the first derivative, dy by dt, this will be sy of s. Okay, so you can see we are multiplying by s here into y of s minus y at 0, which is the initial condition. Let's go one step forward and see the Laplace for the second derivative. So with the second derivative, it will be s squared y of s minus s y of 0, y minus y prime 0 without the s. So you can see the s to the power 0, and then s to the power 1, and then s to the power 2. Okay, so let's go one step as well, just making it like little more complicated. If you go to the third derivative, you're going to have s cubed into y in the s domain minus s squared into y 0, and here you're going to have still s y prime of y prime 0 minus s to the power 0, which does not appear, and you're going to have y double prime 0, and so on. You can go on and on. To make this simpler for you, we are going to deal in our processes with deviations, with differences. What do I mean by that, and what does that imply in what I'm trying to explain here? So, for example, again, for the example of a CSTR. So, if you are changing this valve from 20 to 30% opening, so because you have changed it from 20 to 30% opening, what will happen is that this height will be higher. So it will go higher and higher just because you opened up 10% more. And you heard me, I said 10%. And what we are trying to say here, that the change of that output was because of the change of that input of 10%. And for example, this changed from 3.5 till 4 meters. So we are talking about a change of 0.5. Okay, we are talking about a change of 0.5. So a 10% caused a change of 0.5 meters. And this generalization is not that accurate, but it is good enough for control purposes later. So what I'm trying to say here, that if I have the change of 10 to 20%, I would expect to have a change of 0.5 meters. Okay, so I'm simply saying that if I have a change of any 10%, I'm going to have a change of 0.5 meters. So what I'm trying to deal with here, I'm trying to deal with deviations. Okay, so we are going to deal with deviations in all of our course, and for control purposes later, it will always be dealing with deviations. What does that imply in this Laplace thing that we have taken? So we have shown you that is the Laplace. That is the Laplace of differential equations. So what does that imply here and reflect? What I'm trying to say here is that we are going to deal with deviations. So what do we mean by deviations? So what is the deviation of y in the initial condition? The deviation says that you are subtracting the new value minus the old value, and the old value is the value that it was initially standing at. So the old value was y at 0 time, and the new value is the value that it went through. In this case, for this term, if you want to put it in a deviation format, you're saying that you're trying to subtract it from the initial condition, which is also the same value. So it will cut out into 0. So if you put this in a deviation format, this will be 0. And every initial condition minus the initial condition that it is sitting at will also be 0. And here we can see that things are going to be much easier, and it will be shortened to simple terms. Simple terms, that means for y of t, and I'm going to do that again just to feel comfortable about it. So Laplace for y of t, a normal y would be y of s. And Laplace of y prime, I mean the first derivative, is sy of s. And taking the Laplace of the second derivative will be s squared y of s, and taking Laplace of the third derivative will be s cubed y in the s domain, and so on. So now our life is easier, and this is very easy to be memorized. So what we are going to use, we are going to use all of these Laplace terms in our problems. So I would expect that now for you to review this Laplace transform, starting that you're changing all what we have in the time domain, changing all what we have in the time domain to the S domain. We don't need to know the mathematics of it, but you need to know the main terms. Even though that you're going to have the Laplace table, you need to know the main terms, and one of those terms is the just a value, which is a step input, or a t, which is a ramp input, or a sine input, or a cosine input, or an input that could be not input, or an output, which usually is represented in an exponential term, and we should know how it looks like in the S domain, and an output which could look like something which is stable or something that is unstable, as we can see here, or the impulse input. So all of these we need to know how to convert to time or to convert it to S domain. So talking about Laplace and Laplace inverse. And then we need to know, of course, we're going to take the Laplace transform of differential equations to solve it. And taking to differential equations, we are going to have these terms to be appearing in an algebraic format. Finally, so Laplace transform, I would like to write that in white. So Laplace transform helps us to take everything into an algebraic format. And of course, if everything is in the algebraic format, it's easy to solve, and actually it will be easy to analyze as well, and we can do a lot. And so the next step that we are going to go through, we need to go through this, we need to apply this Laplace transform to the time domain system, the model equations of the different processes that we have mentioned. Remember that Laplace transform is a linear operator. So what I'm trying to say here is that we need to do one step to do Laplace transform. So if we have a nonlinear system, we need to do some kind of linearization. And because we want to study differences, we need to put it in deviation format. And after that, we can say we can apply Laplace transform to get our S domain in the algebraic format. All that we're going to do in our next lecture, hopefully in lecture number 12. So happily, we are very happy. We have finished lecture number 11. So see you in lecture number 12 to apply Laplace transform to the different systems, the CSTRs and the mixer and the search tanks. It's going to be enjoyable. We just started applying our systems into real life applications. See you, good luck, and wish you all the best.